My name is Despina Hatzidimitriou. I'm a professional astronomer and I work as an associate professor in observational astrophysics at the Department of Physics of the University of Crete. I'm also a senior researcher at the Skinakas Observatory, which is located on the island of Crete in Greece. I have served as president of Commission 37 of the International Astronomical Union for star clusters and associations. In this video presentation, I will show you how to use CCD images of globular star clusters to derive their ages. But first, I will give you an introduction where I'll discuss different aspects of globular cluster research. Globular clusters are among the oldest radiant objects in the universe. They are regarded as fossil records of the earliest epochs of galaxy formation, including that of our own Milky Way galaxy. They are impressive, gravitationally bound concentrations of thousands to hundreds of thousands and even millions of stars, spread over a relatively small volume of several tens to about 200 light years in diameter. It is widely accepted that stars do not form in isolation, but result from the fragmentation of molecular clouds, which in turn leads to star cluster formation. The stars belonging to a globular cluster have different masses, but they have practically the same age and chemical composition. The stars in a cluster orbit around the center of the cluster, and the cluster itself orbits around the center of the parent galaxy. Their compact sizes and large masses make them readily observable in external galaxies. Historically, the first globular clusters were discovered in our galaxy, the Milky Way galaxy. The first globular cluster, M22, in the constellation of Sagittarius, was discovered as early as in the 17th century. The discovery was apparently first made by the German amateur astronomer Abraham Mil in 1665, while he was observing Saturn in Sagittarius. It was described as a composite nebula. The term globular cluster was first used by Sir William Herschel in the 18th century. The discovery of M22 was followed by that of the southern cluster Omega Centauri by Edmund Halley in 1677. Several more globular clusters, which were still classified as nebulae, were discovered during the 18th century by Gottfried Kirch, Edmund Halley, Jean-Philippe Lois de Chezeaux, Charles Messier, William Herschel and others. Messier's catalogue, first published in 1771, contained 29 globular clusters. Charles Messier was the first to resolve a globular cluster into stars. William Herschel, on the other hand, resolved virtually all of the then known clusters into stars and introduced the term globular cluster to describe them in 1789. He discovered several new globular clusters, bringing the number of known globulars to 70. All these objects belong to our own Milky Way galaxy, of course. Today, there are about 158 known globular clusters in the Milky Way. Larger galaxies can have more. Our nearest spiral galaxy, Andromeda, has about 450, while some giant elliptical galaxies may have several thousand globular clusters. Globular clusters are valuable tools for theoretical and observational astronomy across a wide range of disciplines, from stellar interiors to cosmology. They are the observational foundation for stellar astrophysics and stellar evolution. They are used to constrain the star formation and assembly histories of galaxies and nucleosynthetic processes governing chemical evolution. They have been used successfully to estimate fundamental quantities such as the initial mass function. They have aided us in setting the extragalactic distance scale. They provide limits on the age of the universe. They help us understand the role of dark matter in the formation of structure in the early universe and the distribution of dark matter in present-day galaxies. There are several characteristics of globular clusters that have rendered them astrophysical tools of such importance. They are easily recognizable. We can measure their distances, ages, and chemical abundances with remarkable accuracy. They are abundant in all kinds of galaxies. Among them, we find the oldest radiant objects in the universe, and they trace the bulk of the star formation history of the universe. I shall now briefly describe some of the major achievements of globular cluster research. One of the most important early contributions of globular cluster research to astrophysics is in understanding stellar evolution, one of the greatest astrophysical triumphs of the 20th century. Star clusters form the ideal testbed and provide almost the only real constraints of stellar evolution theories. Moreover, they are among the best tools to study extreme stellar populations, such as X-ray binaries or blue stragglers, both of which are likely products of dynamical interactions within clusters. The first breakthrough in our perception of galactic structure was also achieved via galactic cluster research. In 1917, Harlow Shapley determined the distances of globular clusters and used the emerging distribution to locate the center of the Milky Way and to estimate its size. This classic work by Shapley was crucial in that it was the first study of the structure of our galaxy to indicate a center well away from the Sun. Radial velocity measurements have revealed that most globular clusters are moving in highly eccentric elliptical orbits that take them at large distances from the galactic center. Many millions of years are required for a cluster to complete one orbit. They form a halo of roughly spherical shape which is highly concentrated to the galactic center but reaches out to a distance of several 100,000 light years, much larger than the galactic disk. Globular clusters, owing to their luminosity and distinct morphology, have continued until today to play a central role in mapping the shape of the galaxy. A fraction of globular clusters, about 20%, do not belong to the galactic halo, but follow orbits that are nearly circular and are oriented near the galactic plane. These clusters are more metal-rich than their halo counterparts and belong to the so-called thick disk population of the galaxy. Stellar evolution and nucleosynthetic theory have given us the ability to derive the ages of globular clusters and the level of their chemical enrichment, or metal abundances as they are often called. Age and metal abundance information from the clusters, in turn, have provided us with vital clues about the formation and evolution of the Milky Way and other nearby galaxies. The properties of globular clusters, particularly their metal abundances, reflect the properties of the host galaxies. It is generally believed that globular clusters are good traces of the star formation histories of spheroids, early-type galaxies, spiral bulges and halos, in the sense that major star-forming episodes are typically accompanied by significant globular cluster formation. Low-level star formation, on the other hand, for example in quiescent galactic disks, tends to produce few, if any, globular clusters. Because most of the stellar mass in the local universe is in spheroids, globular clusters trace the bulk of star formation history of the universe. Massive star clusters appear to form during all major star formation events, such as those accompanying galaxy-galaxy interactions. Such young massive star clusters, currently being formed in the most violent starburst environments, may be viable protoglobular clusters. The cluster population that we see today in the Milky Way is probably quite different from the original population. Globular clusters suffer continuous change and disruption via tidal stripping and interactions with other massive objects, such as giant molecular clouds, particularly during their passage through the galactic plane and at the closest approach to the galactic center. A significant portion of the original population is believed to have dissolved into the general field population during the billions of years of their walking through the galaxy. Clusters are thus among the basic building blocks of galaxies. The globulars we see now are only the remnants of the original population. However, a process of enrichment of the globular cluster population is also at work through the immigration of globular clusters that belonged originally to satellite dwarf galaxies, some of which may have been cannibalized by the Milky Way during close encounters. Globular clusters are among the oldest known radiant objects in the universe that can be age-dated. The universe is obviously at least as old as the globular clusters. However, deriving the absolute ages of globular clusters is not trivial. The preferred age indicator for absolute ages is the luminosity of the main sequence turn-off, because most theoretical models agree on the onset of hydrogen exhaustion in the cores of low-mass stars. Based on this technique, the most recent estimate, 2009, yields an age of 10.5 to 13 billion years for 4 metal-poor globular clusters. In conclusion, the universe must be at least that old. Recent advances in instrumentation are driving a renaissance in the study of galactic as well as extragalactic globular clusters. New wide-field imaging cameras on several 4 to 8 meter class telescopes offer the unique opportunity to study entire cluster populations to very faint magnitudes in a single pointing, both in the optical and near-infrared. In addition, from Chandra and XMM and GALEX at short wavelengths to the Spitze Space Telescope in the mid and far infrared, our observational window in which to study both the star clusters and the stellar populations are unsurpassed in terms of wavelength coverage and spatial resolution at the present time. Combining the emerging unprecedented understanding of local stellar populations with observations of galaxies at ever higher redshifts, we now are in a position to attempt to constrain the evolution of the basic galactic building blocks throughout space and time. The luminosity and temperature of a star depend on its mass, age, and chemical composition. These fundamental properties of stars are reflected on the color magnitude diagrams of globular clusters. A color magnitude diagram is just an observational Hertzsprung-Russell diagram plotting the magnitude against the color index for a collection of stars. Here we can see the V versus B minus V color magnitude diagram of an old globular cluster. V is the visual apparent magnitude of a star and B minus V is its apparent color, as measured from the difference between the blue magnitude of the star measured through a B filter and the visual magnitude of the star measured through a V filter. The apparent magnitude V is a measure of the luminosity of the star, provided that we know how far away it is and how much of the original light is lost through absorption by interstellar gas and dust, that is, because of interstellar extinction. The color B minus V of the star is a measure of its effective temperature. Large positive values indicate a red star with a cool surface temperature, while negative values imply a blue star with a hotter surface. But the true color of a star is changed by interstellar extinction, which is inversely proportional to wavelength, causing red light to be less affected than blue light. Thus, stars appear redder than they actually are. These effects have to be taken into account when interpreting the color magnitude diagram of a globular cluster. One of the key features of a globular cluster is its main sequence, extending from the turn-off to fainter magnitudes and redder colors. Stars on the main sequence derive their energy from hydrogen burning into helium in the stellar core. In the cores of more massive stars, hydrogen is exhausted more rapidly, therefore massive stars leave the main sequence earlier and at brighter magnitudes. This is the basis of the dating of a globular cluster or of any coeval population. As we have already discussed, all stars in a globular cluster have more or less the same age and same chemical composition. Therefore, the only discriminating factor for the location of a star on the CM diagram is its mass. Therefore, the older a globular cluster, the fainter its main sequence turn-off for a specific chemical composition, simply because even less massive stars have had enough time to spend all the hydrogen in their cores and therefore leave off the main sequence. It has been found that the luminosity of the main sequence turn-off provides the most reliable estimate of cluster ages. Of course, things are never simple. Chemical composition also affects the temperature and therefore color of stars along the main sequence. Clusters with higher metal abundance have fainter and redder main sequence turn-offs at a particular age compared to low metal abundance clusters. This age metal abundance degeneracy means that we need to have an independent measure of the chemical composition of the stars of a cluster in order to derive its age based on its main sequence turn-off. The red giant branch in globular clusters extends from the subgiants, which connect it to the main sequence, to brighter magnitudes and redder colors until the tip of the RGB. Red giants possess hydrogen-burning shells which advance outwards as they ascend the giant branch. The ascent is terminated with a helium flash when helium is ignited in the degenerate stellar core. The shape of the RGB depends strongly on metal abundance. Thus, the RGBs of globular clusters of higher metallicity are shallower and redder than RGBs of metal pool clusters. So, the shape of the RGB can be used to estimate the metal abundance of the cluster, the more accurate alternative being stellar spectroscopy. The horizontal branch consists of stars with helium-burning cores which have evolved off the red giant branch. As we can see, the horizontal branch stars form a strip bluer than the RGB and brighter than the main sequence, with a range of colors but similar magnitudes. The presence of RL-Lyrae variables in the instability strip, the so-called RL-Lyrae gap, is characteristic of all populations, and it allows us to estimate the distance modulus of the cluster. The morphology of the horizontal branch of globular clusters varies. There are clusters with a stubby red horizontal branch, with or without RL-Lyraes, clusters with both a blue and red branch, others with only a blue branch, with or without an extended downward blue tail. We now know that the main parameter determining the morphology of the horizontal branch is metal abundance, and a second important parameter is age, although other factors are also at play. When the helium in the core of a horizontal branch star is exhausted, the core, consisting of carbon and oxygen, contracts and helium becomes ignited in a shell around it. Outside the helium-burning shell, there is a hydrogen-burning shell. The star ascends the giant branch for a second time. The asymptotic giant branch phase, as it is called, is characterized by significant mass loss in the form of strong stellar winds. From the discussion of the basic characteristics of the color magnitude diagram of a globular cluster, we can conclude that in order to measure the age of a globular cluster, we need, on the observational side, a color magnitude diagram deep enough to go well below the main sequence turn-off, a measure of the metal abundance of the cluster, which we can get from the RGB morphology or from stellar spectroscopy, a measure of the distance of the cluster, which we can get from the magnitude of the horizontal branch after correcting for interstellar extinction. Actually, knowledge of the metal abundance is also needed here. Then we need a measure of the interstellar reddening to the cluster, which we can get from color-color diagrams or from the RGB. Assuming we have all the observational data needed, we still need to transform the observational evidence on the main sequence turn-off to an age estimate. This is achieved with the use of theoretical isochrones, which are derived from stellar evolutionary tracks for the appropriate chemical mixture. The evolutionary tracks themselves are constructed using a stellar evolution code, which calculates as a function of time the evolution of a stellar model with a given mass and chemical composition. There are several sophisticated methods device for the accurate dating of a globular cluster, made necessary by the increased quality of observational data. However, we'll use a classical and straightforward age indicator, which has the additional advantage that it does not require direct knowledge of the distance modulus and reddening of the cluster. This age indicator is the magnitude difference in V between the main sequence turn-off and the horizontal branch luminosity at the same color, usually symbolized as delta V. The calibration of this age indicator is achieved via the theoretical isochrones, including theoretical models for the horizontal branch, to set its luminosity, although a combination of theoretical and empirical techniques are used for the latter. Now that you are familiar with the basics of dating of globular clusters, we are ready to start our exercise. The basic data we need are CCD images of a globular cluster through at least two filters, for example B and V. These filters are widely but not exclusively used for the type of work we are describing here. Other combinations that are normally used are V and I filters, or B and R, or B and I filters. I assume that you have installed the software package IRAF in your computer. IRAF is a general image reduction and analysis facility widely used by professional astronomers all over the world. It provides a wide range of image processing tools and it is freely available. In all the following, we run IRAF from a Linux environment. Once you have installed IRAF, you should open an XG terminal using the command xgterm. Now you should go to the directory where the file login.cl is located. You should copy or move your astronomical images into this same directory. Your data files are normally in FITS format. Here we have the files ngc6934v.fits and ngc6934b.fits. Start IRAF from your xgterm by typing CL. As you can see, a list of basic instructions and available commands and command packages appears. The prompt is now CL. In order to run a specific IRAF task, you must first activate the containing command package. For example, to use the photometry commands that we'll need, you must first open NOAO by typing NOAO, then DigiPhot, and finally by typing UpPhot. The prompt has now changed to AP. Now you are ready to start your data reduction. Type !DS9 %. This will open the SAO Image DS9 tool, where you can display your images and perform various interactive tasks. Note the exclamation mark in front of the command DS9. This is necessary whenever you give a Linux command from within IRAF, such as more, mv, copy, rm, etc. Now we type display ngc6934v. To the question frame to be written into, we use the default value 1, unless we have already displayed another image in frame 1, in which case we can use a higher number frame. We can change the display settings in DS9 to improve the appearance of our image. First, we want to see the whole image, so we go to Zoom in the menu toolbar and select Zoom to fit frame. Second, it is usual to invert the color map so that the stars will appear in black and the background in shades of grey. So we go to Color in the menu toolbar and we select Invert Color Map. Third, we can change the scaling of the image in order to see as many stars as possible. So we go to Scale in the menu toolbar and we select, for example, Log, which is usually a good choice. By running the cursor across the image in the DS9 window, while keeping the right button of our mouse pressed down, we can change the levels of the display as desired. You can now see the image of the globular cluster clearly on your window, with its center located near the right boundary of the image. The image is off-centered on purpose in order to facilitate the removal of the galactic foreground stars from the resulting color magnitude diagram without requiring extra images, as we'll see later. Before continuing the analysis, you must perform the basic calibration tasks of bias subtraction and flat fielding, which have been extensively described in the video tutorial Analysis of Astronomical Images, narrated by Dr. Pablo Reig. You will have created two bias subtracted flat fielded images of your globular cluster, one for the B filter and one for the V filter. The files we use here, ngc6934v.fits and ngc6934b.fits, have already been bias subtracted and flat fielded. Now we are ready to perform some preliminary tasks that will give us values of various parameters that will be needed in the following steps. We will use the task imExamine, which is the most useful task when getting started with photometry. The cursor appears on the image on display in DS9. imExamine will display information about the area under the cursor when you hit certain keys. The resulting information appears on your XG turn window or on a graphics window that will open automatically when appropriate. There are two preliminary measurements we need to obtain using imExamine. We shall use four keystroke commands M, R, comma and Q. These commands are issued by just pressing the corresponding symbol on your keyboard while your cursor is on the DS9 window and the window is activated. First, we need to get an estimate of the standard deviation value for the sky or background. To do this, we place the cursor over a random spot on the image with no visible stars, that is, a sky location. We click on the DS9 window to activate the cursor and then type M to print statistics about the area under the cursor. The information will come up on the XG turn window. We note down on a piece of paper or in a text file we can open the standard deviation value sigma for the sky. We repeat this procedure a few times. We can calculate an average value, which we'll need again later. In this case, we get an average around 140. Now we place the cursor over a star. It is better to find an isolated star, neither too bright nor too faint. Stars which have saturated the CCD are not good for estimating the full width at half maximum. We press R, in the activated DS9 window always, to get the radial profile for the star. This appears on the green graphics window that opens automatically. Now we inspect the radial profile. The dashed line represents a Gaussian fit to the data points. As you can see, the stellar profile is well approximated by a Gaussian. Now we need to estimate the so-called full width at half maximum of the profile, which shows you how broad or narrow the profile is. This is an important parameter when you later try to identify stars on your image automatically. We choose by eye the radius which seems to intersect with the value half the height of the Gaussian. Here the value is 1.4 pixels. The full width at half maximum is twice this value, that is 2.8 pixels. We can repeat this on a few other stars. The full width at half maximum should be about the same for all of them, and a value between 2 and 4 is normally fine. Another way to get an estimate for the full width at half maximum is the key command comma, while the cursor is over a star. This will print data about the star, and the last column shows the maximum full width at half maximum. However, it is recommended to view the radial profile using the R key command. Now we can quit imExamine by pressing Q from within the DS9 window. As you can see on your XG term, the AP prompt has appeared again. We are now ready for the next step. We shall run a program called DLFind, which will find automatically most of the stars in our image using parameters that we have to provide. We are first prompted to give the name of the input image. We just check that the default name is the correct one, NGC 6934V. Then we are prompted for the full width at half maximum. We give the value we found earlier, 2.8. Then we are prompted for the standard deviation of the background sky. We give the value we found earlier, 140. Then we are prompted for the detection threshold in sigma. We shall set it at 4. This means that a star will only be recorded if its flux is higher than the sky level by at least 4 times the standard deviation of the sky that we entered just now. If we set a value that is too low, say 2, we'll get a lot of spurious stars. If we set too high a value, say 5 sigma, we may miss a lot of the fainter objects. Some experimentation with this value may be useful. The next 2 parameters, minimum and maximum good data value, can be left at indefinite, so we just need to press enter. Now the program runs and produces a coordinate file with the extension .coo.1, which lists all the stars found by the program. To view this file, which is a normal ASCII file, you can type !more NGC 6934v.coo.1 or open the file with your favorite editor, e.g. Emacs, always remembering to add an exclamation mark in front of a non-IRAF command. You can see that the coordinate file contains information about the parameters you chose. Then it lists the stars it has found. First it displays the x and y coordinates, x center and y center, then the magnitude, mag, some parameters that are related to the image shape, and in the last column it gives a running number for each star. If you run DLFind again, for example to experiment with the parameters, a new coordinate file will be created with a larger running number, for example .co, .2, etc. Increasing the detection threshold, increasing the sky standard deviation value, or increasing the full width at half maximum value will all cause fewer stars to be detected. Decreasing the threshold, decreasing the sky standard deviation value, or decreasing the full width at half maximum value will all cause more stars to be detected, with a greater likelihood of false detections. It is best to try a few settings to attain the best possible results. It is difficult to get DLFind to recognize all the stars that you can see by eye. You can actually inspect which stars it has picked out and remove the ones that look like false detections, or even add some missing ones interactively. This can be achieved with the task tvmark. First we'll edit the parameter file for tvmark. We type epar tvmark. We first give the display number 1 and press enter to move down to the next line. Here we provide the name of the coordinates file, here ngc 6934v.co.1. Press enter until we reach the mark type. Here we can choose, for example, the cross. Then we move down the parameter list, leaving the default parameters, by pressing enter until we reach the color code, where we can put, for example, 207. We move down to interact, where we say no at this stage. We then press ;WQ, which exits the editor and saves the alterations we have made to the parameter file. Now we are ready to run tvmark. As you can see on the DS9 window, crosses have appeared which in most cases lie on top of reasonable stars. However, some may be missing and some may not look so convincing. You can add or remove a few by hand. To do this, we have to edit the parameter file again and change interact to yes. Then we run tvmark again. We inspect the DS9 window. If we want to add a star that looks good but was missed, we go on top of it and hit A. If we want to remove an identification, we go on top of the star and hit the key D. When we have finished, we hit Q, always from within the DS9 window. We can check with the command cat ngc6934v.co.1 that the coordinates of the star that we added have indeed been added at the end of the star list in the ngc6934v.co.1 file. Now we are ready to use the photometry command FORTH. Actually, for crowded fields, such as the inner regions of globular clusters, there are special packages that are specifically designed for crowded field photometry. Such packages are also available within IRAF, for example DLFind. In order to familiarize the student with the basics in photometry, we shall opt for the simpler aperture photometry routine FORTH in the package appFORTH in this tutorial. FORTH is IRAF's basic photometry package. The FORTH task has 5 parameter lists with lots of variables, but IRAF will prompt you only for the critical ones. Entering EPAR FORTH will bring up the main parameter list. The important variables that we need to change are image, the name of the file you are going to do photometry on, output. The default setting will attach a .mag tag to the end of the file name with a number. We'll keep this default value here. Coords, the name of the coordinates list that we are using. By default, it takes the highest number of the .co file. Interactive mode is on when yes is entered. Batch mode is on when no is entered. Here we'll run FORTH in batch mode. Verify. Make sure that verify is on, so that the critical parameters in using FORTH will be verified when you are in batch mode. In batch mode, FORTH will automatically run through the coordinate file that you have specified. You will also be prompted for some vital parameters. You should run FORTH in batch mode unless you want to check your photometry by varying the parameters before saving the results to a file. Let us now run FORTH by typing FORTH. We will be prompted for several parameters. Input image. Enter the image you want to do photometry on, or press enter to accept the one in parentheses if it's the correct one. Centering algorithm. It controls the centering algorithm which finds the star centers. Here we shall choose centroid, the default value. Centering box width in scale units. It controls the size of the box that IRAF uses to find the star centers. The default is 5 pixels and normally it is sufficient. Sky fitting algorithm. This algorithm controls how the sky value is calculated from the annulus. We shall here use the default value, centroid. For the next 3 parameters, we keep the default values. For the standard deviation of background in counts, we give the value we got earlier, that is 140. For the minimum good data value and maximum good data values, we use indefinite, so we press enter to accept the default values. The resulting ASCII file consists of the name of the image with a tag .mag.1. We can view the file using, for example, Emacs. For demonstration purposes, we'll open the file twice in 2 separate Emacs windows. As you can see, there are 30 parameters derived and output for each star. We shall need for future use the values of the star's location, x-center, y-center, the relative magnitude, mag, and its associated error, MERR. We now have the instrumental magnitudes for the stars in the V-band, ngc6934v.mag.1. We must repeat the same procedure for the B-band. This will produce another .mag file, ngc6934b.mag.1, with the B magnitudes and coordinates. The next step is to merge these 2 files. If a lot of spurious stars were left in during the previous steps, then there will be several unmatched objects between the two catalogues. You need to create a file that will include all the common stars with their coordinates, magnitudes and magnitude errors, symbolized with sigma. In order to produce this merged file, you can use a program such as TopCat, which you can download freely, which correlates catalogs, or you can write your own program in your preferred language. The final output should be an ASCII file with the ID number, the X and Y coordinates of the matched stars, the B magnitude of the star, its error, and the V magnitude and its error. You should add a column with the difference between the two magnitudes, that is, the color index B minus V. The running number and the X and Y coordinates will correspond to one of the frames, say the V frame, which will be your master frame. These magnitudes and colors are instrumental. They need to be converted to a physically meaningful scale, that is, they have to be calibrated to a standard photometric system. For the UBVRI filter system, the normally used list of standards are those devised by Arlo Landolt. To perform this calibration, you need to have observed during the same night as your globular cluster observations several photometric standards chosen from Landolt's lists. These stars are usually bright, require very short exposure times, and can be observed even in twilight. You should choose stars with a wide range of colors. We measure the instrumental magnitudes of the standard stars. We know their photometric magnitudes, so we solve the system of equations. Our aim is to derive the values for A1, A2, B1 and B2 and the associated errors. This is an oversimplified presentation of the basic calibration steps. There are several factors that need to be taken into account. Usually, more color terms need to be included. Once we have derived the photometric conversion equations, we apply them to the instrumental magnitudes of the globular cluster stars. We now have created a table with the photometric magnitude V and color B minus V of the cluster stars. Note that the errors must now include the errors introduced via the calibration equations. Normal error propagation techniques should be applied. We are still not ready to create the final color magnitude diagram. The central regions of a globular cluster are usually extremely crowded and may not be adequately resolved with a small ground-based telescope. Even if DLFind has found stars in the inner regions, their magnitudes won't be very accurate, especially since we have not used a special crowded field photometry package. We can limit our further analysis in a ring beyond the core of the cluster. We should now inspect the errors of the magnitudes and colors of our stars. A normal distribution should look like this, with fainter stars having larger errors. You can apply a large error cut to avoid including in your analysis stars with poorly determined magnitudes. Depending on the location of a globular cluster, it may or may not be significantly contaminated by galactic foreground stars. If the cluster takes up most of your CCD image, then you should make sure to observe a close-by region with exactly the same instrument setup and exposure time as the cluster in order to create a comparison field color magnitude diagram. Sometimes it is sufficient to observe the cluster slightly off-center, as we've done with NGC 6934. You should derive the photometry of the stars in the comparison field in exactly the same manner as you did for the globular cluster stars. Then you should subtract the comparison field CM diagram from the globular cluster CM diagram. This subtraction is done in a statistical manner, that is, by dividing the CM diagram in small squares, counting the number of points in the field CM diagram in a particular square, and then removing an equal number of stars from the corresponding square in the globular cluster CM diagram. This is done with the aid of a random number generator. However, it may also be sufficient to create the CM diagram in a ring relatively close to the cluster core, where the percentage of galactic stars may be negligible. Now we are ready to create our color magnitude diagram, from which we'll derive an age estimate of our cluster. We estimate delta V from the CM diagram. Now we need a calibrating equation to derive the age of the cluster. We shall apply here the calibrating equation of Chaboyer et al. 1996. The values of the parameters B0 to B5 depend on the theoretical isochrones used and on the absolute magnitude calibration of the RLI variables as a function of metal abundance. There are numerous observational and theoretical techniques that may be used to derive this relation. Generally, it is accepted that the absolute magnitude of the RLI variables depends on metallicity according to an equation of the form NVRR equals mu Fe over h plus gamma, where mu is the slope with the metallicity and gamma is the 0 point. The 0 point is important for setting the overall absolute ages, while the slope is important in determining the relative ages for globular clusters with different metallicities. We shall adopt here one of the relations used in Chaboyer et al. 1996 and the corresponding parameter values. The metal abundance is also necessary for the determination of the age. It can be derived from the red giant branch morphology, usually from a VI color magnitude diagram, or even better, from stellar spectroscopy. This is beyond the scope of the current tutorial, so we'll take the value of Fe over h from the bibliography. Fe over h equals minus 1.53. Applying the previous equation, we derive an age of 12.3 billion years for NGC 6934. Models and empirical data go through continuous changes and improvements, so you should check the bibliography for updates in the exact form and parameter values of the age equation. Given all the caveats already discussed, the age value we derived should be considered as a relative age and should be compared against the ages of other globular clusters dated in the same way using the same equations and parameters. Absolute dating of globular clusters remains an open field of continuous scientific endeavor, both on the observational and on the theoretical side. We have now reached the end of this tutorial. We learned about the great astrophysical importance of globular clusters, and we went through the basic steps that allow us to estimate the age of a globular cluster.